So this is only one half of the Kasi chamber.
아, 되게 신기하네요. 스피어엑스에 참여하고 계신 한국인 박사님이 계셔서 저희가 모셨습니다. 저곳이 바로 할리우드. 네, 제가 지금 와 있는 이곳은 SPHEREx를 만든 곳이에요. 그래서 조립하기 전까지 모든 실험을 준비를 했던 곳을 저희가 지금 와 있습니다. 그래서 오늘 여러분들과 함께 이야기를 해주실 세 분을 저희가 모셨습니다. So, Dr. Chi, 치 박사님이고, 그다음에 Howard, Dr. Howard. 그리고 여러분들 많이 보셨을 거예요. 강재원 박사님이십니다. So, can you introduce yourself a little bit?
Hi, my name is Chi Nguyen, and I've been working here since 2021. So I have a PhD in astrophysics, specialized in near-infrared instrument. Yeah, so I work with the SPHEREx team, and I'm in charge of the detectors operations, and I'm also involved with the galaxies formation group. So I help them with the low-level analysis, like the detector noise.
That's everything for the science observation, right?
Yeah, so I help my college understand like all of the instrument defects and help them distinguish between the signals from the instrument versus the signal from the sky.
Okay, thank you. And can you introduce yourself?
Hi, my name is Howard Hui. I actually been at Caltech JPL for 15 years. I started out building telescope at the South Pole to look at the cosmic microwave background, to look at the inflation signature from the CMB. And I started working on SPHEREx about 6 years ago. And in SPHEREx, I'm the calibration scientist. And I run a lot of the day-to-day activities in this integration and calibration lab.
강재원 박사님 간단히 소개해 주세요.
네, 안녕하세요. 저 강재환이고요. 하워드 박사님과 같이 남극점 가서 망원경 만들고 관측하는 일 같이 했었고요. 그리고 2020년 가을부터는 여기 스피어엑스 팀에 조인해서 지도를 어떻게 잘 만들까 그런 것을 소프트웨어 개발을 하고 일을 하고 있었습니다.
Can you introduce what is this place?
Yeah, so in this lab at Caltech, we characterize the telescope and the detectors for SPHEREx. So this is the lab where we measure. So the detectors are assembled at JPL across the town from us, and then the telescope was assembled by the vendor, BA System. So when they would deliver, we have a clean room right across the hallway from us where JPL technicians would come there and they would put the telescope and the detectors together, and they put them inside the Kasi chamber, and then they bring that whole chamber over here into this lab. And the reason that we do it in two separate rooms is because the on-of-out space instrument has to be kept in a very clean environment. But in order to have that facility, it's easier to have like a small room where you just have your telescope and your detectors and then put them inside the chamber and then seal up the chamber. And then you can bring the chamber into a regular lab where we don't need to have all of the strict requirements to keep it clean. Like you and I, like we can just like come into the lab and work like this. We have to wear ESD jacket to avoid like the generating static electricity.
Right.
But other than that, we don't have to like wear hand hats. We don't have to wear gloves like when we are in the clean room. So that reduces a lot of the complexity for our lab setup.
That's good. Okay.
Yeah, and here we have like small chamber like that over there. We can take a look at it later.
Yeah.
So those small chamber is used to test the small hardware, like just the detector assembly, as I mentioned earlier. Like you test individual components before you put them together, and you test them in the big Kasi chamber. Back when we had the chamber, like you see like on this yellow tab here, we have optics set up, like a bunch of optics tools here, and then also that optical table over there. So these are different equipments we use. That table over there is for the focus testing. Basically, we use different mirrors, relay mirrors, to simulate a bunch of stars, because we don't have like, you can't like look at out the sky, so you cannot like see actual stars. So we use pinholes and
Make it like
light source.
Artificial stars right here.
And we have a bunch of optics to like transfer that that star field into the telescope. Like so, the telescope would look at a bunch of stars, and then we adjust the position of our stars to see like where the telescope has the best focus. And then we know exactly where the best focus of our artificial star is. And what we try to measure is how much the telescope is offset from that best focus. And then we just adjust the way we assemble the detectors into the telescope. And I'm happy to go over this in detail later if you have more questions.
그러니까 기본적으로 이 방은 뭐였냐면은 스피어엑스 부품들이 개별적으로 다 테스트가 됐던 곳이고 망원경으로 만들어지기 전에 각각의 부품들을 테스트하고 또 그것을 조립하고 다시 한번 테스트하고 그런 실험 장비들이 여기 있고 여기가 원래 스피어엑스가 태어난 곳이라고 할 수 있는 거죠. 이 방이.
That for SPHEREx, because it's a moderate size mission, we only have a fixed focus in the telescope. So we need to make sure that after we launch the telescope in space, cool down to 60 Kelvin, we need to be in focus within 20 micron, so that we put the whole telescope inside a specially made chamber that our Korean colleague that built for us. And inside there, we simulate like space environment. And we have this optical table here that simulate artificial star. And we can make sure that our focus is correct. And we also, then after that, we took the whole telescope out. We shake it at 9G to simulate launch vibration. And we measure it again, make sure that we're still in focus. Another interesting thing for SPHEREx is that we have 25 million pixels. And each of the pixel has a different transmission of spectra. And that's how we measure 100 different color.
More than 102 different colors.
So the way that we need to measure the transmission for every pixel down to 10⁻³ level. And the way that we do that is using this assembly called an integrating sphere in the back and a Winston cone in the front. We feed a monochromatic light inside, and the output of this Winston cone in here is give you a diffuse, uniform monochromatic, so it's only single color, single wavelength light. And we use this to illuminate the entire telescope. And we do that 1 nanometer at a time from 0.75 to 5 micron and look at the response for every individual pixel of the entire 25 million pixel. And that's some of the calibration work that we're doing. And another very important stuff that we need to do, because we want to study the galaxy formation, so we want to look at the diffuse background of the sky. Right. So we not only need to have very sensitive detector, but what we need to know is the correlation, correlated noise between detector detectors.
The structure of how the noise appear in your image. Because in an ideal world, you want a detector that have just white noise, just random noise. Unfortunately, the detectors that we have, those commercial detectors, they actually have some small structure in the noise. It's not
structural noise.
Yeah, in the spatial structure. Yes. So the noise image themselves is never white noise. We whenever you look at it, you can kind of actually see the different stripe in there, because we read them out in columns. And we have 32 shadows that are read simultaneously. So when you look at any image, you can always see 32 sort of column stripe in there. So what we do is we try to measure those stripes as accurately as possible and come up with a formula to describe them mathematically. So then we can look at the signal that we measure when we have actual sky data, and we know how much of that signal is actually from the noise, from the detector itself, and it's not from the sky. So we just account for that.
Yeah, as long as you can measure precisely about the spatial noise, you can remove it, right?
Right, but more importantly, this is special for us compared to other mission like JWST or Euclid, is that our science is not only point sources, but really the diffuse background, the fluctuation in the background. So, and we want to measure really large scale mole, so it's different part of the sky. So we really need to understand our full field of view, how our detector vary in two parts of the sky.
Okay.
Yeah, another way to think about it is what we. So we have two science areas that are actually very complementary to each other. So we have the cosmology, where they try to find the redshift of result sources like galaxies. So they would look at glob of lights that you can detect. And once you mask out those stars and galaxies, you still have the glow left behind. So that glow comes from dust in the Milky Way, dust in the solar system. But that glow also have galaxies that we cannot resolve. There's also starlights that we cannot resolve. So we are interested in the really old galaxies component. So it's part of that light bucket. And the neat thing is that depending on like the redshift of your stars, for example, like nearby stars and galaxies would contribute more to a certain spatial scale. Thus in the solar system, they appear pretty uniform. Like it's kind of like a smooth glow. So those are very easy to remove, whereas the stuff that the glow that are clumpy, those come from stars and galaxies that we cannot resolve. So depending on like the spatial, like what source you're interested in, you look at the specific spatial scale. So the noise that we try to capture, we specifically look at the spatial scale that correspond to the galaxies at redshift above 9.
Can you show us the little bit?
Yeah, so this is only 1/2 of the Kasi chamber.
So it was actually doubled.
It's double. I can show you the other half. So this is actually the front half that is not hosting the telescope, but this is hosting the instrument that behind you. So this is to measure the spectral calibration. So if you come in here, what you see in here is a window. So it's a sapphire window. So sapphire is transmitted in near infrared. So we can have a light beam going inside, and inside the instrument, we have the light going into that instrument, and it's a monochromatic light go in. This is a sphere. It scatters the light to make like a diffuse light source, and at the back, the Wilson cone form a uniform like F1 light cone to match the telescope, what the telescope will see, only one wavelength. And this is one of the tests that we do using the Kasi chamber.
Okay.
Yeah, if you just have a light source and you just like shine it directly at the telescope, the light beam carries some directional information. For example, if you don't want to light them perfectly, you tilt the angle a little bit, that would actually something that we can detect. So in order to remove all of that directional information, like polarization and all of that, we use this whole setup. Just the inside, as you have seen from the other side, is very shiny.
Right.
So whenever light enter one end, it just bounces around a lot. And then it bounces around more, and then by the time it reached the end of the Wilson cone, it lost all of the sense of directions. So then the whole beam just come out very uniform. And the size of the cone is actually very precisely designed.
So this is a mini version of the Wilson cone that I just showed you. So we designed this to map the spectral response of the focal plane, just the detector, without the telescope. So you can see the shape is slightly different because the shape determines the light cone that come out. So without the telescope, we want the focal plane to see a F3 light beam. And this shape, at the output in here, give you an F3 light cone, a uniform F3 light cone that illuminate the entire focal plane. So one of our focal plane is about this big.
If we have a bigger focal plane, and you need a bigger cone.
Okay, I see.
So when we're doing the detector testing, we put this into the smaller chamber.
Right there, the green one, right?
This chamber, you can hear from the sound. It's still continuously running because we want to make sure that if anything happen in space, what we have inside is our engineering unit, engineering detector that she's monitoring. If there's anything question, then...
Yeah, we have to reproduce the problem on the route. And then if we come up with any fix, we have to test it on it first.
Okay. 지금 소리가 계속 나고 있잖아요. 지금 소리가 계속 나고 있는 이유가 저기 챔버인데 카시 챔버의 작은 버전이라고 보시면 하는데요. 근데 이제 카시 챔버는 그 스피어엑스 전체적인 디텍터가 들어가서 저기 안에서 실험을 한 거고, 지금 이제 일단 우주에 보내고 나서 혹시나 생길지 모르는 모든 문제에 대해서 바로 즉각적으로 실험하고 대응하기 위해서 이 칼텍에서 만든 거를 지금 계속적으로 운영을 하고 있습니다.
And I think one of the very unique thing for our experiment is that we have a very small team, and a lot of us.
Yeah, that's what I heard. How could it
Looking
possible?
at 50% of the instrument team currently.
And also, like a lot of us that like building the instrument have half of our job is also like looking into the science. And also, like for people in the science team, we live in the same building. So a lot of the time, we measure like the property of the telescope and of the detectors. We know like what the artifact in our instrument, and we hand it to, like for example, to Jay Huan, and he like used this to make simulation and make pipeline to get ready for the data that we will see. So Jay Huan make the entire pipeline to how do we stitch every exposure together, and like also like looking at like the power spectrum and everything that he can like explain to you in a much better way. So
파이프라인이라는 말이 좀 생소하신 분들도 있을 텐데요. 데이터가 들어오면은 그 데이터를 어떤 프로세스를 거쳐서 의미 있는 데이터로 처리하는 과정을 말하고요. 아까 여러 가지 이미지를 스티칭한다고 했는데 SPHEREx가 보게 될 이미지들 여러 개를 같이 합쳐서 감도가 좋은 지도를 그리는 과정을 말하고요. 아까 말씀드렸던 여러 가지 기기에서 올 수 있는 여러 가지 잡음이라든가 이런 문제들을 스티칭을 해서 지도로 만들어 봤을 때 어떤 효과를 발생하게 되는지 그거를 공부를 해봐야 되기 때문에 그 과정을 이제 시뮬레이션을 만들어서 그 파이프라인을 통해서 이게 어떻게 보일지 그거를 연구하는 과정이라고 보면 됩니다.
파이프라인을 만드는 것 자체가 되게 어려운 일이거든요. 왜냐하면 파이프라인을 만든다는 게 데이터가 사이언스에 이용될 수 있도록 바로 사용자에게 전달을 해주는 그 구축 과정을, 데이터를 정리를 해주는 그 과정을 만들고 계시다고 보시면 될 것 같습니다.
맞습니다. 네.
another interesting fact is like if you look at these doors, they are not the standard height. We have meeting with Kasi and make sure that like how big of a chamber that we can build. And then we come here, we modify the door so that the top of the chamber is barely fit under the door. So originally this door doesn't exist. We make a new door. The reason we built this door is that like right over here is our clean room.
Whoa!
So this is where usually when we're in here, we'll need to put on a bunny suit to make sure this is a space environment. And that chamber is where we put the telescope.
기본적으로 이 방은 클린룸이라고 해가지고 우주와 거의 비슷한 환경을 만들어서 하는 곳이죠. 그래서 이곳에서 망원경 부품, 디텍터를 저기다가 넣고 잠근 다음에 여기서 빼가지고 저거를 이동을 해가지고 저쪽 방에 옮기는 거죠. 그래서 옮겨서 실험은 저쪽 방에서 하는 거죠. 그래서 여기 있는 카시 챔버가 다 지금은 이제 스피어엑스 실험을 마쳤기 때문에 다 분해된 상태에서 이제 다시 한국으로 옮겨질 예정입니다. 아, 되게 신기하네요. Hi, Dr. Hui. Can you introduce yourself first?
So my name is Howard Hui. I'm a research scientist at Caltech and NASA JPL. So I am the calibration scientist for the SPHEREx mission. And so my job is to look at how to build the instrument, and also making sure that it's capable to do the science that we set out to do.
So you participated from the very first time of the SPHEREx, right?
Yes. So I joined SPHEREx when we got selected in 2019. So we've been working on this for the last 6 years.
Okay, very good. 그러면 SPHEREx의 가장 중요한 임무와 목적은 뭐라고 할 수 있을까요?
Yeah, so SPHEREx being like a space mission is really trying to cover a lot of the interesting astrophysics question that we have. So we have three main objectives for this telescope. One is to look at the beginning of the universe, what happened 14 billion years ago, period of inflation, by looking at distribution of hundreds of millions of galaxies. And the second objective is to look at the fluctuation in the background, and to look at when and why when the first galaxy formed. And the third objective for SPHEREx is coming closer back to home within our own galaxy. We've tried to look at interstellar space, that the ice absorption. So this is including water and carbon dioxide, methane, these organic ices, to try to understand how life form. So that's the three main science goal for this mission.
그러면은 다음 질문으로는 어떻게 SPHEREx가 다른 우주망원경과 좀 다른 부분이 있을까요?
Yeah, so the main difference for SPHEREx is like this is a survey mission. So in 2 years of operation, nominal operation, that we're supposed to map the entire sky, 4 times. And every time we map the entire sky, we're looking at 102 different wavelengths. So what we're ending up getting is 102 different like color and of the entire sky. Compared to like other telescope like JWST and Euclid, they will only like survey a very, very small portion of the sky. But for us, we look at the entire like statistical property of the entire sky.
So in that case, what will be the advantage of the searching an entire sky, but not in so much detail? What will be the best advantage for it?
So we designed this really to satisfy the science objective, to look at inflation, to look at like what happened 14 billion years ago. Really need to look at the large scale distribution. So you need to look at like the galaxy distribution in like very, very far apart in the sky. So you need to measure many galaxies very, very far apart.
Okay.
And also for the background fluctuation, very similar. You need to like look at like the large scale mode.
스피어엑스의 데이터, 관측 데이터가 결과적으로 장기적으로 천문학에 어떤 임팩트를 줄 수 있을까요?
So SPHEREx, one major impact for the community is that the legacy data set that we'll release pretty much right away when we have the data. Everyone can use these data sets to look at different science that they want. We, as a science team member, look at specific inflation question, but the entire everyone from around the world can use this data set to do exciting science.
Okay, thank you so much. 이제 두 번째로 여기 스피어엑스에서 근무하고 계신 그리고 기기 개발을 담당을 하고 계시는 닥터 치 박사님을 모셨습니다.
My name is Ji Wing. I'm a postdoc at Caltech. So before Caltech, I worked starting rocket experiment that also used similar near-infrared detector as SPHEREx. So in SPHEREx, I contribute to both the instrument and the science team. So on the instrument front, I specialize in the detector operations. And on the science team, I work on the low-level systematics, so specifically the detector noise.
Alright. 그러면은 스피어엑스의 디자인이라든지 아니면은 기계적인 특징에 대해서 설명해 주실 수 있으실까요?
Yeah, so SPHEREx is a small telescope, so it's actually about this big.
Oh, this big?
Yeah, so it's the primary mirror is about this big, and then we have the whole optics change. So we have 3 mirrors, and then we have a beam splitter that would divide the incoming light into 2 paths based on their wavelengths. So the light with wavelength shorter than 2.5 micron will go in one direction toward one of our focal plane assembly, and the light that is between 2.5 and 5 microns will go toward the other focal plane assembly. So each focal plane assembly is kind of like a camera. So each of them would have 3 detectors. They are near-infrared detectors, similar to those used on the James Webb Space Telescope. The difference is that we have the linear variable filter on top of each detector. So when we capture an image of the sky, every single pixel on our detectors is sensitive to a different wavelength. So essentially, each focal plane assembly is like a spectrograph that allow us to capture both an image of a source as well as their wavelength informations. So when we point the telescope at one part of the sky, you take an image. Let's say you have galaxies that land on one corner of the detector. So we have the information of that galaxies at the wavelength that corner is designed to be sensitive to. And then the telescope would change. We steer the telescope a little bit, so now it points to it move a little bit, and that same galaxy is going to land on a different part of the detector, which is sensitive to a different wavelength. So now we get image of that galaxies, but at a different wavelength. So that's how we gather both the image and the spectral informations at the same time.
That's very impressive. So we can see at the spectrometer and imaging at the same time, right? I know that the CASI contribute somehow in the SPHEREx, right? So what's the role of the CASI and how you collaborate each other?
Yeah, that's a great question. So CASI actually contributes to both the instrument as well as the science aspect. So their biggest contributions on the instrument front is that they design and build a big chamber for us. Telescope and detector are supposed to work in space, so we have to simulate the space conditions. The telescope supposed to be at 60 Kelvin in order.
60 Kelvin.
Yes, in order to minimize its all thermal emissions. Our detectors also have to be at between 60 and 45 Kelvin in order to make them more sensitive to the near-infrared sources. In order to have you need some chamber in order to put the whole instrument, the telescope and the detectors under vacuum and then cool them down to their operation temperature in order for us to characterize how our system works when it's that cold. Now, CASI designed a chamber that fit our telescope, which is great, and then they ship it to us, and they come and help us. They teach us at Caltech how to put the chamber together, how we put the telescope inside, how do we read out the temperature at various parts inside the chamber. So they did all of that design, and they just taught us how to use it. Yeah, and on the science front, they help us understand some of the calibrations data. They help us. So we do the calibration, when we make the measurement, you have to reduce the data, and the two teams do it independently, and we come together and we confirm that we get the same result. That's one nice thing. So they help us during the spectral calibration campaign. They also contribute to the simulation, the sky simulator. Basically, we have some software to help us simulate this is what we expect to see in the sky. So we have some CASI member working on that simulations for us. They incorporate what we've learned from the instrument into the software so that the software can actually reproduce those instrument defects. And they also contribute to the ISIS science. So CASI is an important contributor to the ISIS team as well as to the source, galaxy source selections. They review a lot of existing sources that is known to astronomers, so galaxies, stars, nebulas. So they review all of those and pick out the one that would be useful for us to calibrate our instrument, those that would be useful to do the first light survey, first light image. And they contribute to the ice science, so they are also expert in searching for signatures of ice in the Milky Way.
다음으로 여쭤보고 싶은 거는 이 스피어엑스를 개발을 하면서 특히 이 기기들을 개발을 하는 업무를 담당을 하셨는데 이 기기들을 개발을 하시면서 가장 어려웠던 점이 뭐가 있을까요?
Yeah, so we do have a lot of challenges that the team come together to overcome. So one challenge was due to the pandemic, a lot of the design of the CASI chamber has to be done entirely remotely. So team at Caltech and the team at CASI have to talk our telecom once a week for 2 years. So it's actually pretty amazing that they designed a chamber that fit our telescope perfectly. We also have some challenges in learning to use our detectors because the experiment is designed to study cosmology with the precisions that no other infrared telescope has done. So the team had to put our best effort to understand the instrument defects really well in order to help us pick out the extremely sensitive, extremely faint signal from the skies. And a lot of what we're doing nobody has done before. There are no other near-infrared survey in this specific spectral window, and there are not many, we don't have the data set to study the galaxy formations with the level of sensitivity that SPHEREx is going to do. So we really, the team really do our best to understand our instrument.
All right, perfect. Thank you so much.
Thank you very much. Thank you.
스피어엑스에 참여하고 계신 한국인 박사님이 계셔서 저희가 모셨습니다. 사실 저희 안될과학에도 여러 번 출연을 하신 강재환 박사님인데요. 먼저 간단하게 자기소개 한번 부탁드리겠습니다.
네, 감사합니다. 강재환이고요. 현재 칼텍에서 2020년부터 박사후 연구원으로 일하고 있고 그동안 스피어엑스 사이언스 팀 멤버 일원으로서 파이프라인을 만드는 그런 일을 하고 있었습니다.
이번 스피어엑스에는 그러면은 지금 이 맡은 역할이 이제 파이프라인 개발을 하고 계신데 개인적으로 어떤 연구를 하고 계세요?
앞서서 이제 3가지 연구 주제를 크게 나눠서 말씀해 주셨는데요. 인플레이션 주제가 있고 그 다음에 이제 은하들이 어떻게 진화하는지에 대한 연구가 있고 그다음에 얼음 입자들이 어떻게 어디서 만들어지는지 연구가 있죠. 그 중에서 이제 저는 은하진화에 관련된 부분에 제 연구를 하고 있습니다.
그럼 이번 스피어엑스 개발하는 데 있어서 그다음에 발사하는 과정에 있어서 뭐 주위의 여러 연구진분들과 함께 참여를 하셨는데 그 중에서 가장 어려웠던 부분이 있을까요?
가장 어려웠던 부분이라고 하면 데이터에서 이제 저희 과학 연구를 위한 그 자료로 정리하는 그 과정을 처음부터 다 만들었어야 했거든요. 그래서 그 과학 주제에 해당하는 그 소프트웨어를 만드는 데에 이제 처음부터 만들다 보니까 그것을 같이 의논하고 개발하고 하는 과정이 아무래도 어려웠던 과정이었던 것 같습니다.
그러니까 기존에 없던 소프트웨어를 스피어엑스에 맞게 처음부터 지금 개발을 했어야 되니까 무에서 유를 창조하다 보니까
네, 그래서
어려움이
처음에
많으셨겠네요.
생각했던 것들이 이제 안 되고 앞서 이제 보셨던 많은 장비로 실험하는 이런 것과는 또 다르게 한편으로는 파이프라인 만드는 것도 실험의 과정이랑 어떻게 보면은 그러니까 연관적으로 생각할 수가 있을 것 같거든요. 어떤 시도를 해봤다가 또 안 되면 이제 다른 방식으로 넘어갈 수도 있고, 아니면 이런 쪽으로 정리를 했으면 좋겠다고 생각했지만 뭐 예기치 않은 곳에서 뭐 계산이 너무 오래 걸린다거나 이런 것들을 이제 고쳐줘야 되는 상황도 발생할 수 있고요. 그런 것들을 처음에 이제 예측이 안 되다 보니까 하나하나 알아가는 게 난관 중에 하나였던 것 같습니다.
이번 스피어엑스가 발사를 하고 나면은 첫 데이터는 언제쯤 받을 수 있을까요?
우선은 발사를 시작한 다음에 한 달 조금 더 긴 기간 동안 궤도에서 망원경이 잘 작동하고 있는지 여러 가지 테스트 데이터들로 망원경 상황 체크를 할 거고요. 그 뒤에 이제 실제 과학 분석을 위한 데이터를 얻고 그거를 이제 사용해서 저희 팀 내부에서 먼저 그것을 알아보게 될 겁니다.
이 스피어엑스를 기대를 하고 있는, 관심 있게 지켜보고 있는 분들께 한마디 전해주시면, 기대의 한마디 해주시면 좋을 것 같아요.
여러 가지로 세계 최초가 되는 수식어가 많이 붙는 망원경이기도 하고요. 지금까지 보지 못했던 방식으로 우주의 지도를 만들어가고 우주의 구석구석을 탐험하면서 우리가 보지 못했던 새로운 진실들을 알려줄 수 있는 망원경이니까요. 앞으로 들릴 소식 기대해 주시면 좋겠습니다.
네. 나중에 저희 랩미팅에 스피어엑스 관련돼서 한국 방문하시면은 또 여러 가지 초기 결과들을 가지고 한번 들려주세요.
아주 좋은 아이디어인 것 같습니다.
네, 나중에 저희 초청 꼭 모시도록 하겠습니다. 감사합니다.
네, 감사합니다.
네. 반가운 얼굴이 옆에 와 있습니다.
이게 MIT는 써 있는데 뒤에 보면은 이렇게 칼텍 못 들어가서